Hi, this circuit, with a few resistors, is going to help me explain Kirchhoff's laws and how to use them. We will also look at a more complex example later. Now, Kirchhoff, or Kirchhoff as some people call him, came up with two main laws that help us analyse circuits. That is his current law and his voltage law. Kirchhoff's current law states that the total current entering a junction is equal to the total current leaving it. That may seem obvious, but it's helpful to think about, and the key takeaway is that current is conserved. So if, for example, I had a diagram where I had three wires joining to one node in the middle, and I've got current flowing in this direction, and out this direction. Let's say here I have 1 amp, and here I have 2 amps. I know that because the total current entering a junction is equal to the total current leaving a junction, 1 plus 2 means there must be 3 amps leaving here. Kirchhoff's voltage law states that in any closed loop, the sum of voltage drops is equal to the sum of voltage supply. Now, what that means is if I draw a simple circuit with just a DC power source going through one resistor and then looping back around, say this is a 3 volt supply, the sum of voltage drops must be equal to the sum of voltage supply. So because this is a closed loop and there is a 3 volt supply, the drop across the resistor must be 3 volts. Now let's look at our circuit and use Kirchhoff's laws to analyse it. Remember, as always, you can try the circuits I show yourself with the links in the description. So to start off with, let's look at current flow. So we know the supply has the positive side this way around, so current's flowing this direction. So let's just draw a loop for this closed loop here of current flow. And then in this second loop, we know that current is flowing in this direction. So let's just draw that in there. Current's flowing like that. So in this first loop, we know that Kirchhoff's voltage law tells us the voltage supply must equal the voltage dropped. So because there is only a 3 volt supply and only one resistive load, we actually know the voltage drop across this resistor must be 3 volts. Using that, we can use Ohm's law because we now know the voltage and the resistance of this part here. Ohm's law is V equals I times R, or rearranged to give I, which would be I equals V divided by R, giving us 3 divided by 40 equal to 0.075 or 75 milliamps. So the current flowing through this resistor is actually 75 milliamps. Now, using Kirchhoff's voltage law, because there is 3 volts dropped across this resistor and we have a 4 volt supply, we actually know there must be only a 1 volt drop over this resistor. So again, using Ohm's law, we can take I equals V divided by R, giving us 1 over 20, which is 1 volt divided by 20 ohms, which gives us 50 milliamps. So the current flowing through this resistor is 50 milliamps. Now, there's only one more thing we don't know. We don't know the current flowing through here. So for this, let's use Kirchhoff's current law. So if we say the current flowing into here is I1, current flowing into here is I2, the current flowing here is I3, we know that I1 plus I2 equals I3 because Kirchhoff's law tells us that the currents entering a node must equal the currents exiting it. And because we already know I2 and I3, we know that I1 is actually equal to 75 milliamps minus 50, which gives us 25 milliamps. If we now simulate the circuit to verify our results, we can see we have 75 milliamps flowing through this resistor, as we got here. We have 50 milliamps flowing through this resistor as we calculated here, and finally we have 25 milliamps flowing out of the supply. Perfect. Now this next example is going to be slightly more complicated, so I will streamline some of the working so it's not too wordy. So first of all, let's draw some current loops. So we know that the current is going to conventionally flow from the plus to the minus, and let's do the same here from the plus to the minus. That's our current flow. Now, we know that the sum of voltage drops equals the sum of supply, but in this circuit we have at least 2 resistors in every loop, so we can't get a quick start like we could in the previous circuit. So instead we're going to have to form some equations. So let's write an equation to describe the voltage in the first loop. So let's label the current flowing into here I1, the current flowing into here I2, and the current flowing out of here I3. Now let's try and make an equation that describes the voltage drop in this circuit using Kirchhoff's voltage law. So we know that the supply, which is 5 volts, must equal the drop. So V equals I times R, so we've got 10 times I1, so 5 equals 10 times I1 plus 40 times I3. 40 times I3. And then for our second part of the circuit, we have 6 equals 20 I2 plus 40 I3. Same again. Now, because of Kirchhoff's current law, we know that the total current entering a junction must equal the current exiting a junction. So we actually know that I3 is equal to I1 plus I2. So if we simplify both of these and remove I3 by replacing it with I1 plus I2, we can instead get 5 equals 10 I1 plus 40 I1 plus 40 I2, and 6 equals 20 I2 plus 40 I1 plus 40 I2. Then we can then simplify this a little bit to give us 5 equals 50 I1 plus 40 I2, and 6 equals 60 I2 plus 40 I1. Now, if you remember from your simultaneous equations, we want to find a like term so we can cancel them. So the quickest way to do that in my mind is to multiply this line by 3, multiply this line by 2. That will give us 15 equals 150 I1 plus 120 I2, as well as 12 equals 120 I2 plus 80 I1. Now we have 120 I2 in both equations, so we can get rid of them. So I'm going to speed up the simplifying a little bit here, but that gives us 15 minus 150 I1 equal to 12 minus 80 I1. And if we then simplify these, that would give us 3 equals 70 I1, giving us I1 equals 3 divided by 70, which put through a calculator gives you 42 milliamps. So the current flowing through this resistor here is 42 milliamps. Now, if you wanted to work out the current for the rest of the circuit, you could do it using the equations we've already created. So up here we have 5 equals 10 I1 plus 40 I3 here. So if we replace our 3 over 70 with I1 and solve to get I3, if we now clear the template, but remember that I1 equals approximately 42 milliamps, or 3 over 70, and that our first equation was 5 equals 10 I1 plus 40 I3, we can actually use these two equations to calculate I3. So first of all, let's just redraw I1, I2 and I3 with their arrows pointing like so. And then let's combine these two equations. So we should end up with 5 equals 3 over 70 times 10 plus 40 I3, which when simplified gives us 5 minus 30 over 70 in brackets all divided by 40, which gives us approximately 114 milliamps. That's I3. I1 is 42 milliamps. We haven't worked out I2 yet, but we can actually do that using Kirchhoff's current law. If you remember, we already know that all the current flowing into a node is equal to the current flowing out of a node. So we actually know that I3 equals I2 plus I1. So we can take 114 minus 42, giving us roughly 72 milliamps. That's 72 milliamps of current equals I2. Now let's try simulating the circuit and see how we did. So you can see that through this central 40 ohm resistor, the current I3 is 114 milliamps. Through this resistor over here, the current throwing I2 is 71 or roughly 72 milliamps. And the current flowing on this side is roughly 42 milliamps. Perfect. If you wanted to work out the voltage drop across any of these resistors, you could, because you already know the current and the resistance, so just use Ohm's law. Overall, Kirchhoff's laws are absolutely fundamental for anyone studying electronics. Thanks for watching, be sure to like the video if you liked it, subscribe if you loved it, and have a good day. See ya!